Hello, so we are now with activity 1.5, dealing with voltage amplifiers and the concept of loading. And in this activity, we are asked to derive an expression for the output voltage across a load, RL, when the input of the amplifier is a voltage source with an open circuit voltage, Vs, and an internal source resistance, Rs. And then we have a practical example where we are going to start plugging in numbers. Okay, so let's draw our model of the amplifier. Ri. We are modeling the amplification with a voltage controlled voltage source. We are modeling the fact that we have a finite output impedance and a finite input impedance. So here we have our amplifier model. This is our input. This is our output. We are going to connect it to a source, a voltage source. Yes, it has a finite internal source resistance. This is basically the Thevenin equivalent of either a source or a previous stage. And we are also supplying this output voltage to some other circuit, which is our load circuit, and RL is effectively the Thevenin equivalent looking into the NAS circuit. Okay. So what we are asked to do is to derive an expression for the output voltage for this circuit. Let's do it. So the output voltage, the voltage at this node, assuming that this is our ground, V output, it's pretty straightforward, right? We have a voltage divider. If we know the voltage here, we have a voltage divider. Now, what is the voltage there? This is AV times V input, right? The voltage source amplifies with the open circuit voltage gains whatever we sense here at the input. So, well, the output then is simply RL divided by RL plus R out times the voltage here, which is AV times V input. Now, let's continue, because this is not the source input. So we have RL plus R out, AV, and now at the input we also have another voltage divider. And this is because we have a finite input impedance. If in our amplifier we are drawing some current. So what is the voltage here? If we know the voltage there, well, it's a voltage divider again. Ri plus Rs times Vs. So we got our expression for the output voltage as a function of the input voltage. Now let's make here a couple of annotations. Now, this is the output loading. And as you know, it's going to be less than 1, right? RL divided by RL plus something else is going to be less than 1. It will only be 1 if equals to 1 if R out equals to 0, right? And over here, we have the loading due to the input. Input loading, which also is going to be less than 1 and will only be equals to 1, right, if Rs was equal to 0 or Ri was equal to infinity, right? So our expression for the output voltage, therefore we can say V output is equal to the open circuit voltage gain, a reduction due to the output, a reduction due to the input, and the original voltage. So let's do this practical example now. Now, in this example, we say, well, we have an input impedance in this amplifier of 5 kilo ohms. We have a gain of 200. We have an output impedance of 100 ohms. We have a load of 300 kilo ohms, and we have a source with 2.5 kilo ohms. Okay, so before doing this analysis, ideally, what will we want? Ideally, we will want the output to be equal to AV times the source. This will be the ideal if we didn't have any loading. By the way, loading. Let's have a working definition for loading here. Loading. Loading is a reduction in a voltage level, right, at any point due to the relative value of the resistive network that you have, or the impedances. In the context of amplifiers, we could say a reduction in gain due to the interaction of the amplifier with the external circuit. Amp with external circuit. It's not just really turns out to be a reduction in voltage level because of the interaction of the amplifier with the external circuit. So ideally we will want, what was our gain? 200. What was our source input? 30 millivolts times 30 millivolts, that's equal to 6 volts. If we didn't have loading, or if we had designed the amplifier to work well with that source and that load, we should have something close to 6 volts. Now, let's see the effect of loading. We have V output, 200. Now, we have 300k divided by 300k plus 100, and this actually is going to be close to 1. The problem is not so much in the output, but it is significant in the input, where we have 5k divided by 5k plus 2.5k, right, times 300 millivolts, and this is approximately, right, equal to 3.998 volts. So, as you can see, we have lost a significant amount. Now, how do we improve it, right? How can we improve it? Well, How do we do it? We increase Ri and decrease Rout. Now in this case, we will want that Ri is greater than 100 times, sorry, Rs, and that Rout is less than 100 times smaller than Rout, than RL, right? And in this case, we are there. Now, this is a general rule of thumb, right? The ratios depend on the time, how much tolerance you have. If, and I'm going to leave this as an exercise, assume that we have an Ri that is 100 times Rs and an Rout 100 times less than RL, and do the analysis and see how close you get here. You will see that you get the 5.9. With that, let's look at the next activity. Cascading amplifiers. Now that we have done the loading here, we can start thinking about, well, what happens when we cascade two amplifiers? What happens to the gains? Really, you can always think about this part being part of an amplifier and this part of another one, but we want to see if we have another one here with a gain, what's going to happen? With that, thank you.